Hi, my name is Dr. Levi Tegg. I'm a postdoctoral research associate at ACMM at the University of Sydney, working under Professor Julie Kearney. Today, I'll be reporting on our progress towards using nanoporous copper tips as frameworks for analyzing frozen liquids in the atom probe microscope. So why is this necessary? As we all know, atom probe microscopy is a very powerful microanalytical technique, but historically it's been limited to dense conductive specimens due to the high vacuum and high voltage environment of the instrument. The development of the laser pulsed atom probe enabled the analysis of semiconducting and insulating solids. This extended the technique to geology, the semiconductor industry, and increasingly to hard biological media such as bones or teeth. But the nanometer scale chemical information that atom probe microscopy provides would be valuable in analyzing soft matter, which includes liquids and solutions, polymers, and soft biological materials. Collectively, the methods for analyzing soft matter fall under cryo-APT, protocols and procedures for the cryogenic preparation of samples and their cryogenic transfer into the atom probe microscope. Several groups have made advances in this area recently. The groups at Deakin and Monash universities in Victoria have been using graphene to encapsulate liquids. A pre-sharpened tip is lifted through an eyelet holding the analyte solution with a graphene layer floating on top. The group at Pacific Northwest National Laboratory have reported on mixtures of water ice with borosilicate glass. The outermost layers of the glass are porous, with water penetrating into the pores and hydrating the glass. A sophisticated fib lift-out procedure is used to prepare specimens for atom probe. The group at Stuttgart cooled tungsten wire to cryogenic temperatures and then fractured it, creating a rough tungsten surface. They then deposited water onto the end and used cryofib to produce a specimen suitable for atom probe. They've also used this method to analyze glucose solutions and other organic liquids, highlighting the versatility of this technique. The penetration of water into pores or onto rough surfaces is important in the second two examples, as the rough substrates are highly wettable for aqueous solutions. This is exemplified in the work from the group at MPIE in Dusseldorf, who deposited water onto a nanoporous gold substrate, plunge froze it, and then used cryofib to produce a single-phase ice tip. Field evaporation of water and ions occurs from the single-phase apex, but they also show that water penetrates into the nanoporous gold layer. Nanoporous metals are conductive, rigid, and highly wettable, which made us wonder, what if the entire tip was nanoporous? Could we load water into the pores, then cryo-transfer it to the atom probe, and use that as a method for analyzing frozen liquids? Here is our proposed workflow. We start with a binary alloy, made from a less reactive metal A and a more reactive metal B. We section this alloy into matchsticks and electropolish it using conventional means. We then dealloy the tip by immersing it in an acid which selectively dissolves the reactive metal B, leaving behind a nanoporous framework of the noble metal A. We then dip the nanoporous tip into a liquid, such as water or aqueous solutions, and then plunge freeze in liquid nitrogen or ethane and cryo-transfer to the atom probe. Looking ahead, we're looking at using copper as the more noble metal, and I'll talk about why in a second. First, why are we bothering to investigate this procedure when the existing procedures have returned such great results? There are a few reasons. The first is that we're hoping to avoid cryofib in the long term, because this can be a significant bottleneck against high throughput analysis of samples. Second, the metal framework should increase the conductivity near the apex, which will hopefully avoid sample fracture. And this should mean that samples can be analyzed in voltage mode. This is important as we want to keep the 0 to 60 Dalton range clear for the molecular fragments from our evaporated liquid inside the pores. In the classic nanoporous metal system, gold-silver, nitric acid is used to etch away the silver, leaving behind nanoporous gold. The gold-silver alloy is not easy to electropolish, and the evaporation field of gold is quite high. Studies from Elzoka et al. Have shown the evaporation field of water is quite low, and we'd like to match the evaporation fields across the phases in our sample to avoid distortions in the reconstruction. So we've been searching for alternative alloys. The ideal alloy and metal needs to satisfy several important requirements, including straightforward synthesis, ideally with inexpensive metals, be easy to section and electropolish, have good chemical stability in air and water, and ideally have few isotopes with low evaporation fields. But it turns out Not many alloys satisfy all of these requirements. Not many systems strike the balance of differing reactivities, mutual solid solubility, and having low evaporation fields, and low cost and high availability. The first we investigated was nickel manganese. Ammonium sulfate can be used to selectively remove the manganese, ideally leaving behind a framework of nanoporous nickel. Overall, it worked, but oxidation was a major problem at every processing step: sectioning, electropolishing, and dealloying. The image shows a fib trench cut showing nanoporous nickel, but with pervasive oxides inside the pores. The lesson learned from this is that the more noble metal needs to be more noble. So, we tried a similar system: copper manganese. As before, the dealloying acid dissolves the manganese, ideally leaving behind nanoporous copper. We were able to prepare this alloy using an induction casting furnace. Unfortunately, two interpenetrating FCC phases were observed on cooling, each with a different manganese content. This image shows an electron backscatter detector image of a polished surface, with the colored overlays representing chemical maps generated using EDS. This result was interesting and led to some nice micrographs, but it's a problem for us because we expect different dealloying rates in the manganese-rich regions to the manganese-poor regions. This will lead to larger pores and inhomogeneities at length scales far greater than what we're looking for. Still, we thought it was worth a go. Per literature methods, this alloy can be electropolished with phosphoric acid and dealloyed with several acids, but so far we've only tried concentrated ammonium sulfate. What's shown here is the dealloyed coupon of the parent alloy. Zooming in on the paler region reveals a large domain of nanoporous copper. In contrast with the nickel manganese sample, the nanopores are widespread throughout the sample and are relatively free of oxide. The ligaments are around 20 to 40 nanometers in diameter, and the pores are about half of that. But these diameters should be able to be controlled with the acid and with the dealloying time. This is exactly the sort of structure that we're hoping for our nanoporous tips. Sydney has been under lockdown since June, and without access to laboratories, experimental progress has been very limited lately. So for now, I'll talk about our next steps. We'll be focusing on copper manganese going forward, mainly due to the greater chemical stability of copper, but also because it has fewer isotopes, a low evaporation field, and tends to evaporate in its 1+ charge state, leaving the low Dalton part of the mass spectrum relatively clean. But there are still some major challenges to overcome first. We need to make a single-phase alloy, as the differing manganese content of the two FCC phases have different dealloying rates. There's also a lot of improvements to be made in the electropolishing and dealloying conditions. Still, with the nanoporous structures I showed on the previous slide, we're looking at doing a remote fib lift-out to see how resilient these structures are to the ion beam and to platinum deposition. After we've mastered the synthesis and the fabrication, we can start to look at more big-picture jobs. We build the protocols for loading water and plunge freezing, and continue to make advances in cryotransfers for atom probe. We're particularly interested in characterizing the temperature of a sample as it moves through our cryotransfer system. Later on, we can focus on optimizing the acquisition conditions inside the atom probe, such as the specimen temperature, the pulse rate. Other researchers have made some impressive advances in this space, but we still think there's plenty to be learned in terms of optimizing acquisition conditions. And that's it from me. Thanks for watching. I'd like to acknowledge the group of Professor Julie Kearney, Sydney Microscopy and Microanalysis, Sydney Manufacturing Hub, and Microscopy Australia. I'd also love to hear what you think, so if you have any questions or suggestions, you can catch me in the networking session on Monday evening Pacific time. You can also send me an email at the email address shown, or you can reach out on Twitter. Thanks.